Hey guys, it's Mr. Los. Welcome once again. Today we're going to talk about solution stoichiometry, and as you guys can see, I really went all out for you here, guys. I'm getting a little fancy. Got some word art going here. Some of y'all know what I'm talking about. You know, you like to mix in a little word art with your projects, get them fancy looking. I have this picture. You know, we were talking in the last video about Kool-Aid Man. I have this picture that I drew of two Kool-Aid men, and one shooting laser beams out of his eyes and shooting a tree. And I know what you're thinking. You're thinking, gee, that's a really weird picture, Mr. Los. What's going on with that? Well, it's a long story. I didn't draw it for this. I just happened to see it. I was looking through some files I had, and you know, we were talking about Kool-Aid Man, and I thought, why not? I wish you could see this in color. I don't have a color printer. That would truly, I think you'd appreciate my artwork a little more. But anyway, we're talking about solutions. We're talking about stoichiometry, two of my favorite subjects. You're going to need, as usual, you're going to want a calculator. You're going to want a periodic table handy, a page in your workbook. It looks like this up at the top. I've got some stuff written on this one already, but it should say solution stoichiometry. It starts talking about molarity and so forth. So that's one of those pages that you're going to need from the workbook. So make sure you gather that stuff out. Oh, of course, a calculator. But don't be afraid to pause the video for a second and grab that stuff if you need it. This is just the following page. Okay, so what I'm going to be kind of doing is talking you through kind of the beginning part of this page. We're going to work through these example problems. And there's some really important concepts here. So, first of all, when we're dealing with solutions, okay, these aren't pure substances, these are solutions, mass is not particularly helpful. Like, I thought these two things were so important, I decided to write them on a page and print them out to show them to you, so they must be important. When we're dealing with stoichiometry, as you guys know, hopefully, it's always all about moles. We got to get to moles somehow. You really can only find moles if it's a solution from volume and concentration, not, as it says above, mass. Now let me explain to you what I mean by that. Suppose you had a glass of salt water, a salt solution, not a pile of salt, but salt water, and you knew some particular reaction required 10 grams of actual NaCl. Would you take the salt water and actually weigh out 10 grams of it to get your 10 grams of salt? Think about that for a second. Think about the answer and what the answer might be. Did you come up with no? Good job. Yes, of course, you would not actually weigh out 10 grams of salt water, because that 10 grams of salt water, what you'd be weighing is mostly water, and there would only be a little bit of salt in that. If you wanted 10 grams of NaCl, you would need however much of this solution contained 10 grams of NaCl, which would be quite a bit more than 10 grams of the solution itself. We'd have to figure it out. The only way we could figure it out is concentration. If we knew how concentrated the solution is, then we could figure this out. Then we could figure out how much of the solution it would take to weigh 10 grams. And when you think concentration, think about that Kool-Aid that we made. You drank the concentrated Kool-Aid, you drank the not-so-concentrated Kool-Aid. With the concentrated Kool-Aid, it takes less of the Kool-Aid to get the same number of grams of the Kool-Aid, if you catch my drift there. And remember our concentration units, molarity, and IB's mole per cubic decimeter. So, as it talks about there at the beginning of this page, molarity is really helpful to do stoichiometry with. Of course, in the IB world, we're kind of stuck with mole per cubic decimeter. But out of the different concentration units that we talked about, like percentage, mass percentage, and so forth, these two are by far the best because they can relate the substance directly to moles. So, again, referencing your workbook page, it goes on to talk about an example of NaCl. So suppose we had 2 mole per cubic decimeter NaCl. So this is our solution. You know, we got that salt water I was mentioning earlier. We got a little bottle of salt water. On the label says this. Now, what does this really mean? It means there's 2 moles of NaCl in 1 cubic decimeter of solution. Remember, a cubic decimeter is the same as a liter, of course. So one of our jobs when we do stoichiometry, if we're going to do stoichiometry by dimensional analysis using conversion factors, you can always take a concentration and change it into a conversion factor to do stoichiometry. What this concentration means is it means there's 2 moles of NaCl in 1 mole, or rather 1 cubic decimeter of solution. It's a conversion factor just like 18.01 grams of H2O equals 1 mole. Except this time, instead of, like we said, masses aren't helpful. Instead of relating moles to mass, we're relating moles to volume. Usually in IB, like on all IB tests, and most of the time you're going to get mole per cubic decimeter as your concentration unit, although we will see, if you study further chemistry and in this class, you'll see molarity sometimes. So if we have a bottle and we see this is what the label says, 0.1 molar HCl. It's not pure HCl, it's an HCl solution. Well, what that means, remember molarity is moles per liter. What that means here is that there's 0.1 moles of HCl per 1 liter of solution. Now, of course, mole per cubic decimeter and molarity are the same, as we've talked about, so we could talk about this in terms of cubic decimeters or whatever. The other thing I would make a reminder of real quick is just remember that a cubic centimeter is the same thing as a milliliter, and a cubic decimeter is the same as a liter. So when you convert between them, you move the decimal over 3 spots. Just as a review here, remember, so 100 cubic decimeters, rather 100 cubic centimeters, if I wanted to change that to cubic decimeters, I'd move the decimal over 3 spots, 0.100. I say this because we're always going to want to use cubic decimeter in these problems. Okay, so with that setting the stage there, we are going to get started. Wait, I don't know how that got there. Okay, so I have these example problems. These are the same ones that are on your workbook page, and we're going to take a look at them. Okay, so it says, suppose 100 cubic centimeters of a 1.5 molar HCl solution is added to excess magnesium. How many grams of hydrogen gas will be produced? All right, let's see if we can decently focus. I guess you can sort of see it. Okay, so when we're doing a stoichiometry problem, the stoichiometry problem it's all about moles. We got to look at this problem. We got to see where am I going with it? Where do I need to go with it? Pay attention to the details, like the state symbols, for instance. We got to understand when we're dealing with solutions, when we're dealing with solids. All that stuff is important. Like, you ignore these little things, you're going to get yourself in trouble. So let's kind of map out what the problem is giving us here. Okay, so we're dealing with an HCl solution. I can tell that from many ways. It gives me a volume because it says aqueous here. So it says 100 cubic centimeters of that, and it gives us the concentration, 1.5 mole per cubic decimeter. And then what it's asking us for is question mark grams. So, like on any kind of stoichiometry, you always want to get to moles. Like whether we do it with grams or whatever, on all we're going to do a variety of different kinds of stoichiometry problems. But in all of them, it's the same basic concept. You got to figure out a way to get to moles so that you can use this. You can use this equation and you can use this ratio. We got a 2-to-1 mole ratio here. So the difference between the other, what some of you will be tempted to do is look up the molar mass of HCl and try to turn this into a mass, but that is not helpful. Okay, this is not pure HCl, so the molar mass of HCl doesn't help us. The mass of this solution doesn't help us because this solution is mostly water. We have to get to moles a different way than we did in our other stoichiometry problems. And we're going to do it from the solution and the concentration. But once we change this to moles, then it's a stoichiometry problem just like any other ones that we've ever done. Okay, so first thing I'm going to do is I'm going to change this concentration into a conversion factor. So my conversion factor, and I'll just write it up above here, I know there is 1.5 moles of HCl in 1 cubic decimeter of this solution. So that's the conversion factor that I'm going to use. I also know that I have 100 cubic centimeters. What I'm going to do right off the bat is I know that I'm going to need cubic decimeters. Pretty much whenever you're dealing with solutions, you need to work in decimeters or liters, not cubic centimeters. So I'm going to change that 100 cubic centimeters to cubic decimeters. Got to move the decimal over 3 spots. So that's 0.100 cubic decimeter. Okay. So I think we're ready to start here. I want to go from HCl to hydrogen. So I'm going to start with the amount of HCl that I was given. 0.100 cubic decimeters. And I'm going to change that to moles because I always want to use moles in stoichiometry. Here's my conversion factor. What goes up must come down. I want the cubic decimeter to cancel out, so I put it on the bottom. I put the 1.5 moles of HCl on top. Cubic decimeters cancels out, and we're in moles of HCl. Now that right there, that concludes the new part. That's the only thing new. Now everything is the same. We got to think about mole ratio and all that stuff. You know, the same concepts of stoichiometry still apply. Okay, so what comes next is mole ratio, always at this point. So 2 moles HCl for 1 mole hydrogen. So remember when we do the mole ratio, we're looking at the coefficients. This is a mole of HCl on top. So we're going to put 2 moles HCl on the bottom. We're going to put 1 mole hydrogen on top. That again, that just comes from the mole ratio there. So moles HCl cancels, and the question is asking us for grams. So I need to find the molar mass of hydrogen. We use our periodic table there. 1.01 times 2. Hopefully all of us are good at finding molar masses at this point. So my conversion factor is 1 mole is 2.02 grams. Okay. So since I've got moles of hydrogen on top, I'm going to put 1 mole on the bottom. I'm going to put 2.02 grams on top. Now, that's it. Moles cancel. We're left with grams. That's the appropriate unit. And now it's just time to crunch the numbers. So 0.1 times 1.5, that's 0.15. Probably only 2 significant figures here, so 0.15 moles. And then we got to divide that by 2, 0.075 moles. And then we got to multiply 0.75 times 2.02. And so I think that should come out to something like 0.1515 grams. 2 significant figures here. grams. Okay, so there's our first problem. I'm going to do a couple more with you, but if any of that freaked you out, maybe go back, take another look at it, or wait for the next example and see if it can make a little more sense. Now there is probably one alternate way you could solve this, which is this. Well, actually, let me get into that on the next problem. Okay, here we go. Next problem. I'm sorry it's a little blurry. I'm trying to make it better, but it doesn't seem to be cooperating. Similar problem to the last one. This time it's just giving us the more common, in America anyway, milliliters and molarity. But we're going to do the same thing. So 350 milliliters of 0.75 molar HCl, or CaCl2 rather. So that's this stuff. So let's kind of map out what we got. We got 350 milliliters, and the concentration of that solution is 0.75. Again, we're not going to look up the molar mass of this. It doesn't help. This is a solution. It's mostly water. Mass doesn't help us. The only thing that helps us is the volume and the concentration. Now, we know this. It's a 0.75 molar solution, so molarity is moles over liters. So what this implies is there's 0.75 moles for every 1 liter of solution. So that's our conversion factor. I'm just right off the bat going to change this to liters, so little milliliter to liter conversion, move the decimal over 3 spots. Pretty much got to be in liters when you're working with solutions, so we're going to change that to 0.350 liters. And then ultimately what it's asking us for here is grams. So we need to know grams of that. So like in most stoichiometry problems, we're just going to start off with what the problem gives us. I'm going to start off with the volume, 0.350 liters, and instead of using a mass to get to moles, my route to get to moles is going to be the volume and the concentration. So use this conversion factor. I'm going to put 1 liter on the bottom, and I'm going to put 0.75 moles of CaCl2 on top. Liters cancel. Again, that ends the new part of solution stoichiometry. Now it's all the same. Now it's mole ratio and mass. In this case, the mole ratio is 1:1. Now this step is not mathematically necessary, but it's always, because it's a 1:1 ratio, but it's always good to show the step, show you all your work, make sure you're always thinking about mole ratio. Who knows, there might be a working point for it. If this is the IB test, you might actually get a point for showing that, so you might as well do it. Okay, so moles here cancel out, just got the 1:1 mole ratio, so now we need the mass. Now we do need to know the molar mass. This is not a solution, plus it's asking us for grams. So we need to add up the molar mass of calcium carbonate. So that's 1 calcium, 1 carbon, 3 oxygens. We use our periodic table, we add that all up. Calcium carbonate's molar mass is real close to 100. We'll call it 100.06 is about what I came up with. So there's my conversion factor from converting grams to moles. And there we have it. Now it's just a matter of actually solving this out. So we multiply 0.350 times 0.75. That's 0.2625, I do believe. Usually in IB, you're best off just to round. We should have 2 significant figures here, just to go ahead and round off on each step. That's what they would do in the mark scheme. The answers to a real IB exam, they round at each step, it seems like. So that's what I'm going to do here as well, as opposed to just keeping it all in your calculator and rounding at the end. 0.26 moles. Mole ratio is 1:1, so same number of moles of calcium carbonate. So 0.26 times 100.06. We're only going to have 2 significant figures here, so 0.26 times 100.6. It's basically 0.26 times 100. You're going to have 26 grams there. Now, I mentioned an alternate way of solving this. The other way of solving this is sort of from an algebraic perspective. If the mole ratio thing just kind of screws you up, or you don't like that, you could use the molarity formula to find moles in this first step. In other words, get the information from the problem, 0.75, that's the molarity, and solve for moles. We still need to change milliliters to liters, so 0.350, and then you solve for moles that way, and you're going to get 0.2625, and then you'd have to remember to put it into the mole ratio and just go that way. It's the same thing. It's just that if you're more comfortable with algebra, in the first step you can do this, use the molarity equation, find moles, and carry forth that way. Or you can do the dimensional analysis. It doesn't make any difference. It basically just switches up the first step a little bit. If you wanna do that, if you like using the molarity formula, you just got to sort of translate these IB style units into the more familiar ones. So you got to say a cubic centimeter. Okay, I know that's a milliliter. 1.5 mole per cubic decimeter. Okay, that's a concentration unit. So again, we could use the molarity formula in this one. 1.5 molar. Put in my liters here. That's milliliters. I got to change to liters. 0.1. Solve for moles. You're still going to get 0.15 moles, and then you would just carry forth with the math that way. So either way, it doesn't matter. So let's look at one more example here. Okay, this one's slightly different, but the same concepts will apply. What volume in cubic centimeters of 1.75 CuCl2 reacts with 5 grams of aluminum? So this time it's giving me this mass, and it's saying question mark cubic centimeters. It wants a volume, and the solution has a concentration of 1.75. Okay, so what we need to know, normally like the stoichiometry problems that we did at first, it would have given us grams of this, and then it would have asked for grams of CuCl2. But as we know, with a solution, it's much more convenient, or what we really should be dealing with solutions is volume, so it's asking me the volume that I need. So we're going to do the same process. We're going to think about dimensional analysis, and we're going to think about our units canceling out properly, and we're going to get us there. This time we want to end up with a volume. Make our conversion factor here 1.75 moles in 1 cubic decimeter. Okay, that's my conversion factor for the CuCl2. The difference between this problem is I'm not going to use that till basically like the last step. What I am going to do is I'm going to start off with this 5 grams of aluminum. And I look at the periodic table. And I look up aluminum's molar mass. It's 26.98 grams. So there's my conversion factor. What goes up must come down. Gram on top here means gram on the bottom here. 1 mole of aluminum is 26.98 grams. Grams cancel. What's next? Mole ratio, you say? Great job, ladies and gentlemen. Glad you said that. Mole ratio is 3 to 2 this time. So we got aluminum on top. We want aluminum on top, that means we want aluminum on bottom. Now moles of aluminum cancel. We're gaining on it, guys. We're getting there. Okay, so we want a volume, remember, this time. Here's my conversion factor. Now I got moles on top. I want to put moles on bottom here. So that takes care of that conversion factor. Now these moles cancel. So then it's just a matter of solving this out. So it's 5 divided by 26. We could do 5 divided by 26.98 to start. So that's 0.185 moles of aluminum. Mole ratio is 3 to 2. So I'm going to multiply this by 3 and divide by 2. You can also multiply everything on top divided by everything on the bottom. There's a bunch of ways you can get the same answer here. But I'm going to take 0.185 times 3 divided by 2, or times 3 halves, or times 1 1/2, or whatever you want to say. So at this point, 278 moles. And then I got to divide that by 1.75. So then we're going to get like 0.1585, whatever. We need 3 significant figures here. So let's call it, what's my unit? My unit that's left over is cubic decimeters. Let me scoot that up a bit. Okay, so we've pretty much done it. We've got a volume. The only thing is this problem asks us for cubic centimeters, and we're given cubic decimeters here. This is the same as liters, remember? This is the same as, basically it's asking us to turn to milliliters or cubic centimeters. So we move the decimal over 3 spots. So we get 159 cubic centimeters. Okay, so that's all the examples that I'm going to work through for you in detail. I do have one that I'd like you to try. Again, if you're struggling, back up, maybe watch part of this again, see if it can make some sense to you. Of course, ask me next class, ask a classmate, phone a friend, do what you need to do, but you can get there, ladies and gentlemen. You all can do this, I know that. But let's just try it. So what I'd like you to do is take a look at this one. Now this one is not anywhere in your workbook. This is a special problem made specifically for this video. So why don't you take a second, pause the video, see if you can figure this out, and we'll come back in a second. Okay, so here we go. Let's take a look and see how we did. Here we have me. I made a mistake in this first one. That's why they put erasers on pencils, folks. And even I make a mistake from time to time. So let's take a look. We want to change this to a conversion factor. That's kind of our initial stuff. Change this to cubic decimeters. By the way, guys, I'm going to do this dimensional analysis, then I'm going to show you really quickly that alternative method that I meant, or that I said you could do. Change that to 0.5 because we want to work with cubic decimeters. Change that concentration into a conversion factor. And then from there, start off with the volume. Use this conversion factor here. Cubic decimeters on top, put it on the bottom in the next step. Remember, this is my barium hydroxide. So that's BaOH2. So moles of barium hydroxide at the top. The next step is mole ratio, which is right here. It's 2 to 1. Moles of barium hydroxide goes in the bottom. Moles of H2O goes on top. So then your moles of barium hydroxide cancel. You find the molar mass of H2O. That's 2 hydrogens, 1 oxygen. Remember, don't use this 2 when you find the molar masses. The molar mass should add up to 18.01. That goes on top. So it's everything on top divided by everything on the bottom, which should turn out to be about 4.50 grams right there. And that's it. So hopefully you got that. If you got it, good job. I think you can call it a night here. But I'm going to, if you're still struggling a little bit, I'm going to show you this different method, and it's only a little bit different. But the only other thing you could do that's maybe a slightly different approach is to take an algebraic approach in terms of finding the moles and using the molarity formula. Now what this requires you to do, especially if you're given these IB style units here, is do some translating. You got to understand that 500 cubic centimeters is the same thing as 500 milliliters, and that 0.250 mole per cubic decimeter is the same as molarity. So that's my molarity. I still need to find moles. This is still stoichiometry, so I need to use my equation to find moles. So that's 0.250, that's my molarity. I want to solve for moles, so that goes on top. My volume has to be in liters, so I'm going to change this milliliters to liters, which is 0.5. And this is barium hydroxide, remember that we're talking about. So multiply both sides by 0.5, solving for moles. I'm skipping the algebra there a little bit, but hopefully you understand how to solve that. 0.125 moles barium hydroxide. So once we have that, that's really the only part that's different. Then it still is stoichiometry. Next part of stoichiometry is always the mole ratio. It's 2 to 1. So I've figured out my moles of barium hydroxide, so now I can use my mole ratio to go to moles of H2O. And since barium hydroxide is on top, it has to be on the bottom here. And then I need to go to a mass of H2O, so I look up H2O's molar mass, I add it up on the periodic table. And we're going to get the same answer here, 0.125 times 2 times 18.01 divided by 1. You still should get 4.5 over there. Okay guys, so that's it. We'll be practicing with this in class, so hopefully that made some sense to you. If not, we'll talk about it next time and we'll get it figured out. Thanks for watching, and have a good night.